Hello, this is the Section 12.2 lesson. In this section we're going to get our very last type of a hypothesis test. For this lesson you're going to need your calculator. To illustrate this type of test, let's suppose that we're a farmer who grows cucumbers, and we have 4 different patches of cucumbers. Each we treat in a different way. One patch we give both fertilizer and irrigation to, another one we only irrigate, another one we only fertilize, another one we give no treatment at all. Question we might ask is, do these 4 different populations have the same mean weight? Each cucumber patch would be a different population of cucumbers. So do these different populations have the same mean weight? So to test that, we went out and we selected 5 cucumbers from each patch and weighed them. So for instance, from the patch that received irrigation only, the first one weighed 0.23 pounds, the second one weighed 0.04 pounds, so on and so forth. So I have 4 different samples of cucumbers, 1 sample from each of my populations. Each sample contains 5 cucumbers. Well, the claim that we're going to formally test here is that the different treatments have the same mean. In this case, we're going to have 4 different parameters. As we have 4 different populations, we have 4 different population means. Mu1 would be the mean weight of all cucumbers given no treatment. Mu2 would be the mean weight of all cucumbers given fertilizer. Mu3 would be given irrigation only. Mu4 would be given both. Again, we stress the word all there in all those cases because we're comparing these 4 different populations, not just the 5 cucumbers in each one of my samples. So the claim in mathematical notation is going to be the same as the null hypothesis. It's the statement that mu1 equals mu2 equals mu3 equals mu4. Now the alternative really isn't terribly important, but it's the statement that at least one of those population means is different than the others. So let's real quickly look at the analysis here. If we're comparing means, the first thing we want to do is calculate sample means. So there you see our sample means 0.184, 0.332, 0.164, and 1.334. First thing we want to do is just compare those sample means, and notice that they're not all the same. We have 2 that are about the same. We have 1 of 0.332 that's quite a bit larger, and then we have 1 of 1.334 that's quite a bit larger than all the rest. The fact that not all of those sample means are equal is what we call variation between the samples. Well, when we compare sample means, we also need to look at sample standard deviations. We made that point in section 11.3. And so below that we have our sample standard deviations S of 0.127, 0.565, and 0.126, and then 0.895. Those sample standard deviations are sometimes referred to as variation within the sample. Now if you notice, we've got 2 of them that are fairly small, another one that's larger, and then that 4th one of 0.859 is quite a bit larger than all the rest. Now the fact that that one is large and quite a bit larger than the rest is significant. That 4th x bar of 1.334 is an estimate of mu4. The fact that that estimate is larger than all the other estimates indicates that maybe mu4 is larger than all the rest. Well, the fact that the corresponding sample standard deviation is so much larger than the rest would make us not as confident that mu4 really is larger than the rest of them. So the idea behind the analysis here is that we're going to compare the variation between the sample means to the variation within each sample. So we're going to compare those sample means and take into account the sample standard deviations. And this type of test is what's called analysis of variation, which is kind of a scary sounding name first time you see it. The calculations, the formulas are very complicated, so we're just going to let the calculator do the work. Again, it's called analysis of variation, which is abbreviated ANOVA. So in our calculator, we first need to enter our 4 different samples in lists L1, L2, L3, and L4. So to do that, hit Stat, Edit, and then under Edit, you can enter the data. So there you see lists L1, 2, and 3 in the left window. In the right window you see list L4. Again, L1 would be the weights of those cucumbers given no treatment. L2 would be given irrigation only, so on and so forth. So just enter the data as you see it there. Now, once you have the data entered, select Stat, Tests, and then option H, ANOVA. Now, some calculators that may be option G, but it should be there. So when you select that option, back at your blank home screen, it will paste the command ANOVA and then an open parenthesis. Next, you have to enter the list containing the data. So you enter L1 by selecting second 1, and then the comma, which is right above the 7 key, and then L2 by pressing second 2, and then comma 3, etc. Once you have it entered, as you see it in the middle window, hit enter, and you should see the screen that you see on the right. And it gives a lot of outputs. The only one we're really interested in there is the second one, p equals 0.007. That's our p-value. So now we are going to interpret this in the same way. The p-value is less than 0.05, and so we reject the null hypothesis. We word the final conclusion the same way. The original claim did contain equality because it's the claim that all of those population means are equal. So we're to the right. Do you reject it? Yes, we do. So there is sufficient evidence to warrant rejection of the claim that the different treatments have the same mean. So those 4 different populations do not all have the same mean. Now, so stated another way, the different treatments appear to produce different weights of cucumbers. Now, our analysis does not tell us which one of those means is different than the other. Just by looking at the sample means, it would indicate that mu4 is greater than all the rest, but we'd have to do a little more analysis to confirm that. So we conclude that they are not all the same. Now, this word treatment in this situation has a real physical meaning because we treat the different patches in a different way. But the word treatment is really a generic name. It's also called a factor. It's a property or a characteristic that allows us to distinguish the different populations from one another. So treatment is just really a name for each one of those different populations. That's really it for this lesson. I just want to quickly talk about the final project. As mentioned in the syllabus, there is no final exam. You'll have a final project, which is going to be an application of topics from chapters 8, 9, 11, and 12. The description is sent with the syllabus. It's a 2-page description. The basic idea there is that you're going to make a claim about a population, collect some data, and then apply an appropriate hypothesis test. Now, where you get the claim is totally up to you. You do have to collect the data yourself and then apply the appropriate hypothesis test. So here's some possible project topics that you might select that you do ANOVA for. One claim is that 4 different brands of bottled water have the same mean volume. Here we're comparing 4 different populations. Populations would be these different brands. So you could go out and select maybe 5 bottles of water from one brand, 5 different from another different brand. Somehow measure their volume, and then do an ANOVA test to it. Another one is that different colors of M&Ms have the same mean weight. So here you have 6 different colors of M&Ms, so you have 6 different populations. You could select like 5 red ones, 5 blue ones, weigh each one on a digital scale, collect your data, and do an ANOVA test to it. Those are just some examples. Again, you can get project ideas from wherever you want. That's it for this lesson. The Course Compass homework is titled Section 12.2.